handout copy of the talk at that address. Hopefully it's downloadable. I'll be talking today about our recent paper with Jethro, whom I see in the audience, and George Andrews. It's a very, very elementary statement. We just find a PVW basis for a module of the Virasoro algebra that you know. And the proof is completely elementary. So I'm not sure if I'll take the full hour. I think I can always say something. But I wanted to point a couple of problems that are interesting related to this work. So let me get right to the point. So given the password for this seminar, I figured I should start with this slide. So this is the Lie algebra, the Virasoro Lie algebra that I care about. We're going to be studying representations of this Lie algebra. I'm going to be studying only one representation of this Lie algebra. So this is an infinite dimensional Lie algebra. You have it there by generators and relations. And whenever you pick one complex number, you can induce a representation by declaring that all the generators for n bigger or equal than -1 kill that vector, or that vector vacuum, and that the central element acts by multiplying by that complex number C that I'll call the central charge. So that module, by definition, has a PVW basis. It's very simple to see that it consists of monomials of this form, where these lambdas are natural numbers that you can order them to actually get a basis, and all of them have to be bigger or equal than 2 because n-1 already kills this vacuum. So that module is graded. It's graded by declaring the degree being the sum of all the parts involved in this lambda. And since, well, it's a very simple monomial basis, it's very easy to compute the graded dimension of this basis. So that thing there is the generating function for the graded dimension of that module. I can't really say much more than that on the uninduced representation of the Virasoro algebra. I can say something, yeah. So we'll need so fix n, and you're looking at basis of elements such that, of these monomial elements, such that the sum of these parts lambda sum up to n. So that's the space of energy n in this module. But even if you fix the energy n, you can still count these monomials. You can count this number k. And that thing gives you a filtration. That's the PVW filtration, which is an increasing filtration. But it's going to be useful to take this other filtration that is just the negative of the PVW filtration shifted by n here, so that it just becomes graded in a nice way, the associated graded. But the filtration is very simple. You just count the number of parts minus twice, the energy n minus twice the number of parts. And this is made so that the L-2 lives in the filtered part 0. So now this became a decreasing filtration, and the largest piece has L-2, L-2, L-2. That's the biggest, the leading term in this decreasing filtration. Okay, so those modules are almost never simple. Well, actually, no. Those modules are almost always simple. But if you happen to be rational, the central charge happens to be rational of this form. So this is just for 2 coprime numbers. This module is not simple, and it has one vector at that particular energy here. So this is the product of p minus 1 times p prime minus 1 that gets killed by every generator Ln with positive n. And we don't care about the particular form of this generator, but what I want to say is that we know that at that energy, given the filtration that I just mentioned, this guy here is the leading term of that monomial. And the coefficient of this monomial does not vanish. That's the whole point of this vector. This vector, it's hard to write down. Actually, I think there are no explicit forms for this vector for arbitrary p and p prime. There are some general forms for p is equal to 2 and p is equal to 3. And there's some recurrence forms to write it, but I think there's no closed form for these vectors. But in any case, what we do know is that this coefficient is non-zero, so that the leading term in the PBW filtration is this term. And the simple quotient, if you kill this vector, the quotient happens to be simple. And that's what I will call the minimal model with central charge C. Okay, so again, we write down the character, which is the graded dimension of these guys, and this is an expression that is known as the Fagan-Fuchs, the derivation of the character, and well, there's no reason to describe how you compute this, but you can guess that this, or you know that these things are very well known, the character of both these guys and the character of the irreducible representation of the quotients. So that's an expression for this, the character of this general minimal model. There's plenty of things that we know about these modules of the Virasoro algebra, but there's plenty of things that we don't know about these modules. Here's a picture of that module. You have your vacuum vector in degree 0. There's nothing in degree 1. There's this unique vector L-2 in degree 2. There's one vector in degree 3. But now in degree 4, you have two vectors, L-2, L-2, and L-4. And at some point in this degree, P-1 times P'-1, there's many vectors. There's this one in particular that has all the powers of L-2 times L-2 raised to this power, P-1 times P'-1 over 2. And then there's one linear combination that is not a monomial. It's a linear combination of the vectors here that generates a submodule, and the quotient is simple. Notice that, well, here, I didn't really care about L-1, but in the computing this submodule, you do care about L-1. So L-1 of this vector here is not 0, and it lives in degree, whatever this is, -1. So here's a question, and it's a very basic question. If you start with the monomials L lambda that were a basis for the universal module, this VERC, and you just reduce the modulo, this submodule that you're quotienting by, some of them continue being linearly independent until you hit one that is a linear combination of the previous ones. Get rid of that one. Continue adding monomials. You hit one that is a linear combination of the previous one. Get rid of that one. Whenever you finish with this procedure, at each energy level, you're getting a basis of that energy level. Question: what are the monomials that you're left with? We have a global ordering of these monomials. I gave you the order. It's just partitions ordered by this. We have this PBW filtration. What are the monomials that are left out whenever you do this? And these are modules that are very well known. And there's essentially, I have no clue about how to answer this question. It's such a basic question that, that we do not know the answer. Of course, there are monomial versions for this. So let me give you a monomial basis in a different language for the unique module that I care about, which is P and P prime being 3 and 4. So this is just the Ising model. This is central charge is equal to 1/2. And we can realize explicitly this module in a different way. You take an infinite dimensional Clifford algebra. So these are anti-commutators for psi-n plus psi-n. These guys are half integers, semi-integers. And you again induce a representation by declaring that this vacuum vector 1 gets killed by every positive mode. So now that gives you an infinite dimensional vector space V. If this guy carries a natural parity, you declare these psi-n's to be odd. So you decompose your space into an even piece and an odd piece. And it just happened that both of these pieces are representation of the Virasoro algebra, and both of these pieces are representations for the central charge 1/2. And the piece of which is even, I'll call Vir 3/4. Actually, it's not that I call it, it's isomorphic to Vir 3/4. This is completely irrelevant. This is just to tell you how the action of the vectors Ln, the Lie algebra generators, act on those spaces, and they act by these endomorphisms. We're not going to need this formula. That's completely irrelevant. Just to say that why this is a representation. But here you can see that immediately you get a monomial basis for the Virasoro module Vir 3/4, which is given by parameterized by these psi-n's, right? You need an even number of those, and again you're seeing partitions, but now these are partitions with odd parts. right? And they are all different parts. So now we know that we have a basis of this Virasoro module that is parameterized by partitions of a number n with two different parts of an odd, two different odd parts, even different odd parts. Okay. Okay, so to continue, I need to tell you something about classical limits. I told you already that we have, oh shoot, I'm sorry about this. This should be decreasing. I will care about this decreasing filtration that I defined a couple of slides ago. And yes, again, this is n minus 2k. I rushed today, I guess. This is n minus 2k. This is exactly this filtration that was before. Let me get, this one is the right one. It's a decreasing filtration. And this vector here is in n minus 2k. Need to fix that. Okay. So the associated gradient to both the Virasoro module and the irreducible quotient are naturally commutative graded algebras with a derivation of degree 1. So for the Virasoro module, you see it immediately is this polynomial algebra. Just take the PVW filtration, take the associated gradient is this polynomial algebra in infinitely many generators. And the derivation is defined there. It's just the adjoint action of L minus 1. So it takes the variable L minus n and it gives you back the variable L minus n plus 1. But there's a deeper reason why these are commutative algebras. And it's not immediately obvious that the associated gradient of the irreducible module has to be naturally a commutative algebra with a positive derivation, with a derivation of degree 1. Moreover, these are Poisson vertex algebras, but the Poisson bracket in this case is 0. So now I want to understand that this associated gradient of these spaces. And remember that our module is generated by killing this vector. That was a linear combination where this coefficient is non-trivial. So in the associated gradient, what we can do is the following. We take our infinite polynomial algebra in infinitely many variables. We divide by this leading term. And we divide also by all the derivatives of that leading term. Since these are differential algebras, I can take the derivative of this guy and it's still going to be 0. And this gives me an ideal. This is an ideal that is infinitely generated by this guy and all the derivations. But I'll call this guy finitely differentially. So differentially finitely generated. Because it's generated by one guy and all of its derivatives. And we have a natural surjection from this algebra to the associated gradient of vert PP plus. And it's clear that we have this surjection. This vector here has to be 0 in the associated gradient because, well, the leading term in the Lie filtration is this one that you're seeing. And all the other terms are deeper in the Lie filtration, in that PVW filtration. Okay, so we have this natural surjection for every PMP prime between this easily defined commutative algebra and this associated gradient module. I'll just make one comment. This thing here is the arc space or the algebra of functions on the arc space of a fat point. If you take the polynomial algebra on C on L minus 2 and you divide by this power of L minus 2, the arc space of that is this infinite dimensional non-neuterior algebra that is written here. And what we're saying is that the associated gradient to the Virasoro module is a quotient of that arc space, of that algebra. So this is called the singular support of the Virasoro module. And you have this sub-scheme if you take spectrums in the other direction. And we're trying to understand that sub-scheme. So the question, I'll just enhance the previous question that I had. Before we wanted to answer what are the monomials that were a basis. Now I really want to understand what is that associated gradient. Not only I want to have a basis, I really want to understand what is the kernel of that surjection. And that I claim that these are interesting questions. These are deep questions that entail homological invariance of vertex algebras in general, but in this particular case of Virasoro module. So let me tell you some works that were known. So both questions were known for the case P prime when P is equal to 2. Fagan and Frankel in 1993, I'll give you a different proof in a second, but in 1993, they proved that the monomial basis for the case 2 and an odd, for P prime an odd number, is given by these partitions where the one part and the part coming s minus 1 times afterwards differ by 2, at least by 2. So for those of you who know about partition theory, these are the partitions that appear in Gordon's generalization of the Rogers-Ramanujan's identity. The Rogers-Ramanujan identity are very famous identities, and Gordon's generalized them, and one of the two sides are counting precisely these partitions. And moreover, they prove that this surjection that I just described is actually an isomorphism. It was a question asked, I see Andrew is in the audience, perhaps Andrew will know better. I think Tomoyuki first asked at some point when are this surjection isomorphism, or if it was even possible under nice circumstances for vertex algebras for this surjection not to be an isomorphism. And we proved in a couple of years ago that actually even for Virasoro, most cases are not isomorphic. So this Fagan and Frankel result is the only case where the kernel is trivial for that surjection. So any other case that you want to do for minimal models is going to imply computing something about that kernel. All right, so let me tell you what the program is. The answer is horrible, but the program is very simple. So I'll tell you what the program is to answer both questions. So right away, we answer both questions that I asked in the case of the Ising model. And the program to answer that kind of questions is as follows. You first find a vector in the kernel. And how you do this? You put it in a computer. You put this one you can actually do by hand, but you put it in a computer and the computer will tell you, you already know you can compute easily the character on this side, and you can compute easily the generating function for this other side. So you already know that there is a vector in a particular energy. You put it in a computer and the computer tells you what is that vector. Then you compute the Hilbert series of the ideal generated by that vector. Again, you do this with a computer. We computed it up to energy 200, and we checked that that Hilbert series coincides with the Hilbert series for the Virasoro one. So we figure, okay, that vector has to be the unique vector that generates that kernel plus all of its derivatives. So now you want to prove that the ideal generated by that vector that you found actually is the whole thing. So for that, you need to find a way of finding basis for the quotient of your commutative algebra by the differential ideal generated by your vector. And again, you ask the computer to give you a nice basis. And a nice basis means a basis for this ideal such that the leading monomials of those elements in that basis already compute the right graded dimension. So that you count, instead of like arbitrary elements on the ideal, you only care about their leading terms. And once that you only care about the leading terms, then you're counting particular partitions. The problem became about counting particular partitions. So you count those monomials that appear in the Grobner basis, and to count them, it's a problem because, well, typically what you do is you find some sort of recursive system, you solve that recurrence equation, that you can prove formally that you solve that recurrence equation, and you get a sum that is the partition functions for your Grobner basis that you want to prove is the right basis. So now you're faced with a problem, which is you counted your partitions on this side, you know what the graded dimension of the Virasoro module is on the outside, so you have two functions that are counting dimensions, you can put them in a computer and you check that those series are the same, but now you need to prove that those are the same. So that typically is a hard problem, or at least I don't know. It sounds to me like a math Olympiad problem. You hit it with everything you know until it comes out or it doesn't. I don't see of one particular technique that works. So I'll walk you through this program in the case that we worked out. So let's find a vector in the kernel. So I define this vector, which is in energy 9 in the Virasoro module. And notice that it's in the filtration is in degree 3. So remember that 2 was degree 0 for the filtration. So 3 is 1 and 4 is 2. This is in degree 3. This is also in degree 3. 5 is in degree 3 and 2 is in degree 0. And the Ising model is generated by this vector. For this case, we actually need the full vector, not only this guy. So that's the vector that is singular for the Virasoro module at that central charge. This is in energy 6. And again, Lie filtration is 0, this guy, but it's not homogeneous for the Lie filtration. And that's the complication. So by direct computation, you just subtract from this vector that is in the kernel, this linear combination of vectors that are in the submodule, because we're applying Virasoro modules to this guy that is in the submodule, and you obtain this side, and this side is deeper in the filtration. This guy has degree 5 in the filtration. So you start with something in degree 3, you subtracted something in the submodule, and it's equal to something in degree 5. So this guy here had to be 0 in the associated grade. It's just as simple as that. Just use the commutation relation of the Virasoro. And of course, perhaps this is up to sell something, but of course we do this with a computer as well. I ended up implementing vertex algebras in general in Sage. I think it's gonna be in the next version of Sage Math, the package is gonna be public, but it's already there if you want to compile it and test it. It's very slow, and for some reason, I guess it's Python, but it's much, much slower than Thieleman's package for Mathematica. But it's formally, it allows you to work with any vertex algebra, not generators and relations. So we put it in a computer and we obtain this relation. We know that this vector is in the kernel. So now we want to compute Grobner bases. So remember what a Grobner basis were. I'm taking this infinite dimensional algebra, this non-Noetherian algebra, it's infinitely generated algebra, and I'm dividing by this guy and all of its derivative of this guy. And then I want to take the ideal generated by this other guy. So let's better work directly in this algebra, and let's take the ideal generated by these two elements and all of their derivatives. And we want to compute the basis of that ideal. And you see, it quickly gets out of hand. So you start with A, which is what we were killing first. You take the derivative, and you see this guy. You take second derivative, you no longer have a monomial. The third derivative, well, and this quickly gets out of hand. So it's very hard to compute the general term for this guy. What is very simple, and you guess it immediately, is what are the leading monomials for these guys. You see L minus 3, L minus 2 square, L minus 3 square, L minus 2, L minus 3 cubed. And now you see a pattern. Like you add one, you get the other one, and then you get L minus 4 cubed. And this continues. And what you're guessing actually does continue. The leading monomials are always of the form L minus P cubed, L minus P square, L minus P minus 1, L minus P minus 1 square. And these are all the leading monomials when this derivative. That's what makes Frenkel and Fagin's problem very simple. This was actually generalized. And this is a theorem of Ruszczyk, Murtada, and Shepard, which is not that old. It's 2013, so it's only 5 years before we published our paper. They computed this for the general case of L minus 2 to an arbitrary power. And the leading monomials are those. So if you want to compute a basis for the quotient, then you're counting monomials that do not contain these guys as divisors. So you're counting partitions that satisfy this condition. And this condition is precisely the condition that Fagin and Frenkel found. So this is an alternative proof of Fagin and Frenkel's theorem. Actually, Fagin and Frenkel's theorem never was published, as far as I know. Jethro might correct me. It's a beautiful paper. If you haven't read it, it's beautiful. They prove this identity using coinvariance. They come with an idea that comes from CFTs. They're really thinking about conformal blocks for these corresponding vertex algebras, and they prove this partition identity a la Gordon, Roger Ramanujan. But anyway, so this is an alternative proof. Ruszczyk, Murtada, and Shepard, they computed explicitly what are all the leading monomials for the basis of this ideal given this way. Okay, so now we want to add B to the play. This other new generator that we computed that we know is in the kernel. And now this gets completely out of hand. So you start taking the derivative of B, the second derivative, third derivative, fourth derivative. You say, well, let's look at the leading terms. The leading terms are read in red, and you see the same leading terms that we saw for the derivatives of A. So in principle, you can subtract from these combinations the right combinations of the derivatives of A to get rid of everything that is red here. And then you're going to end up with another monomials where the leading terms are the next ones. So all of these guys should get killed in the quotient because they are going to be leading terms of elements in the ideal. Okay, so what you do is you ask a computer again, can you give me the leading terms of these guys up to a very high degree? And you have to be very persistent to get the high degree enough. These are the leading terms. They are not nice. I apologize, but this is what it is. Typically, when you're computing Grobner bases that come from representation theory, they are horrible. And this is the Grobner base, the leading monomials for the Grobner basis for that ideal generated by those two elements. They are parameterized. I'm writing them in a different way so that you see the partitions. So L minus P cubed, I'll write it as P, P, P. The same guy P appearing 3 times. So this is L minus P plus minus 1 times L minus P squared, and so forth. So in this line here, you see the derivatives of A that I have mentioned. The same part appearing 3 times, the one part, and then the consecutive one, and then one part, the next one, and the same one, and then the consecutive one. So if you were counting everything but these monomials, you would be counting what Fagan and Frenkel counted. Then you start seeing these horrible things, and you get disappointed because you cannot prove your theorem until you realize that actually in degree 31, and only in that degree, this guy here is a partition that lives in degree 31, this thing stabilizes. So you have all of these guys that are there for every P, and these 4 exceptional cases that are in leading monomials for some leading terms for some elements in that idea. Again, you can only do this with a computer, and this is not a proof. You just guess. The computer is not going to tell you these are always leading monomials. The computer is going to tell you up to this degree, these are leading monomials. So now you need to prove that these guys are leading monomials in that idea. And also you need to count them. So to prove them is not hard. You just do it by hand. Well, again, also by computer, but you can do it by hand. And once you guess that this is the right thing, you obtain a monomial basis for the quotient, which is what you want to do, which is compute this monomial basis for this quotient, and it's given by those partitions that do not contain these partitions inside. So there are monomials that are not multiples of these monomials. I'm going to call these partitions P. Those are the partitions that we want to count. So that was the next step in our program. Let's count those partitions. That is surprisingly difficult as well. So now we have our set of partitions that was properly defined before, and you want to count them. And I couldn't find, and I think it's not possible to find a simpler recurrence relation than this one. So we break our partitions in 5 disjoint subsets. We are going to find a related system, a system of difference equations for the generating functions for these subsets. So perhaps I'll say a word. It's not interesting that we have this system. What it is interesting though is that all of this complication and this partition in these 5 different subsets come from the previous slide. In all of these partitions that you need to avoid, all of them start with P is equal to 2. So L minus 2 cubed is 0 because we're killing that vector in the Virasoro guy. Except this one. This is very special. This one starts at P is equal to 3. So the partition 5, 3, 3 is not allowed, but the partition 4, 2, 2 is. And that's why all of these exceptional cases deal with the case that they end up in 4, 2, 2. So since this thing here that starting at P is bigger than 3 is allowing the partition 422, these exceptional guys, all of them end up in 422. And because of the existence of these 4 exceptional guys is that you need to break up that set of partitions P in these 5 different sets where you have a 2 or you don't have a 2. That's A, you don't have a 2. Well, if you have a 2, do you have another 2 or not? And if you have 2 2s, do you have a 4 or not? So those are the 5 sets that you're dividing. And then you find easily recurrence relation between those. The only problem is that you cannot find a way of expressing Cn, for example, in terms of Bn minus 1 or Bn minus 2. You can only find recurrence, or at least we could only find recurrences, if you also count the number of parts in your partition. So this became a hard problem because now if we are going to count these partitions, we're not going to get a 1 variable partition function, we're going to get a 2 variable partition function. And the character of Virasoro had only 1 variable. There's no easy way of adding an extra variable to the character of Virasoro. Okay, so we have a recurrence system and you guess the answer. And this is, I think I can honestly say you guess the answer, unless you're an expert and you have some technique. I am not, we are not. This stage with Jethro, I can safely say that Jethro was also not an expert on this topic. So we just guessed these formulas and they just happened to satisfy the system before with the given initial conditions. There's nothing interesting about this formula except the fact that these are double sums. That's going to become interesting in a second. These are double sums for a particular form. Okay, so now that you know that you have a generating function for each one of these subsets, you sum them all and you get this. So that's a very simple theorem. We counted the partitions that we're interested in, and this is the series that we got. So that series is interesting because of the form that the series has, and I'll get back to that in a second. But this is the partition function for our partitions. Okay, so now that's the main theorem. So let's recap a little bit. So that was the commutative algebra when I divided by A. And now this is the unique vector that we found in the kernel plus all of its derivative. And the claim is that once you kill this extra vector, you get an isomorphism to the irreducible module. The basis for the irreducible module consists of all those partitions Pn. So those are the ones that avoided our horrible set of monomials. And the generating function for our partitions is the one that I just gave you in the previous slide. So since I am telling you that this is an isomorphism, well, we better have an identity between the character of the Virasoro module that has that graded dimension and our partition function. And the only part that is not proven is this one. We need to prove this identity, that the character of the Virasoro equals to our partition function. And this is where we were stuck. We had this conjecture for a couple of months, I think, and we couldn't prove it. We attacked it everywhere. I put it on Math Overflow. I sent it to everyone that I know that knows about these things. I think even Shashank got an email about this identity. And it took Andrews a couple of weeks to come up with a conjecture as to how to prove it. So here's the character of the Ising model. So again, since we want to prove this identity, then we know a lot about the character of the Ising model. So we need to choose one of these sides to try to make it equal to the other side. So here are several expressions for the character of the Ising model. I already told you this line here, this is the Feigen-Fuchs character. This comes by analyzing what are the singular vectors on the universal module. This expression here, you can quickly get it from my description as the even part of the free fermions, right? So you're counting all fermions and then subtracting the odd part. And let's not get to this. This side being equal, the first line being equal to the second line is a very famous identity known as the Jackson-Slater identity. And it has the flavor of the Rogers-Ramanujan's type identities, where you have an infinite sum equals infinite product. it's clear what are these infinite product parameterizing. This is parameterizing partitions with certain congruences modulo 8 and modulo 2. So that's congruences modulo 16. And this side here also parameterizes naturally some partitions known as Hershorn's partitions. What is incredible from this series of identities is the last one. The last one for me is just amazing that physicists actually got this. What does E8 have to do with this? But this is impressive. So, and I'm just putting this last one because this is known as a parafermion or fermionic type partition. This is a quasi-particle kind type of generating series where you have Q to some quadratic expression. Here is the weight lattice of the group E8 divided by a bunch of quantum numbers. The quantum number is defined here in this last line. So whenever you have this set of sums, Q to a quadratic expression given by a positive definite non-degenerate matrix divided by the corresponding quantum numbers here. So this is a sum in 8 parameters. That's known as a quasi-particle sum. Okay, so these are all known theorems. This in particular, I would really appreciate if actually someone gives me an elementary proof. The proof of this theorem is very hard to see, to read. It comes from studying the Bethe ansatz, the particular limit, and then you put it in a box, and then you take a limit of this box going to infinity. It's a very hard proof, this theorem. And it's not surprising that it's hard. What does E8 have to do with the Virasoro module? And this comes from Polyakov's original construction. Okay. So we're going to choose the first of these sums, sorry, this one. And we're going to prove that this guy is our sum. So, well, there's nothing to do about it. This is very elementary. It's just that you need to come up with these polynomials. And this is what our collaborator Andrews did. He just decided, well, just take these two polynomials, Sn, Tn. These are polynomials for each n. But as n goes to infinity, remember, this is a quantum number with n minus k, that as n goes to infinity, this goes to q sub infinity. And then you're dividing by the quantum number also with an n, so that cancels the 2q infinity. And you end up having this q to k, q to the 2k squared. So it's very simple that the limit as n goes to infinity of this Sn goes to one side, which is the Virasoro character. And with the same argument, you just cancel the q infinities on the Tn's, and it's very simple to see that the limit as n goes to infinity of this guy goes to our side of the series. So we had this. Andrews put this in a computer and he checked the first, I don't know how many cases he checked, that they were equal, and say, okay, so these two have to be equal. So now that we have a guess that this polynomial is equal to this polynomial, how do we prove this? And again, we put it in a computer. We put it in a computer, we put it in a package. I should have given this as a reference. We put this in a package from the RISC group called Q multisum. That what it did, it found one recurrence relation that these polynomials Sn satisfy and Tn satisfy. You can check that the recurrence relation is satisfied by both, and you check the first few cases, and that's it. The problem is that this recurrence relation, unless I'm getting this wrong, I think it's of order 9. No one is going to do this by hand. I really wish someone could give me a proof of this identity by hand. The proof is formal. You can formally prove that they satisfy this recurrence relation. But how do you get that recurrence relation of degree 9 of order 9? I wouldn't know how to prove this without a computer. So there's something deep there that I don't understand. Anyhow, so now that's the proof of our theorem. Okay. So the proof is completely elementary, but let me tell you some consequences. Because the consequences are interesting. So we prove this identity, the character of the Virasoro side on this side, and this has nice properties with respect to the modular group. The Virasoro vertex algebra is a rational vertex algebra. Well, the minimal model vertex algebra is a rational vertex algebra. So the characters of the representations are components of a vector valued modular form. And on the other side, you have a sum, as I said before, is q to a quadratic expression divided by these quantum numbers. These kinds of sums are very well studied in number theory. There's a famous conjecture by Nem relating torsion elements of some K group, the block group, with modularity properties of these kinds of sums. So whenever you have the sum for a matrix A, the NAM conjecture goes along the lines of where whenever this matrix A satisfies some conditions, you can find some B's and C such that this sum becomes modular in a way. For example, being a component in a modular form like the character of Virasoro. And since this has been studied a lot, and in our case, this matrix is a 2 by 2 matrix, R is equal to 2 here, it's no wonder that this matrix that we had was studied. In fact, all the matrices of rank 2 that satisfy the asymptotic conditions for this sum to be modular are known. They were classified. There are infinite families, and they all satisfy this NAM conjecture that you can find B's and C's so that this sum becomes modular. And there's some exceptional cases. This was classified by Terhoven, a student of NAM, and then later took by Zagier, Don Zagier. They did extensive searches with computers, and this matrix is one of the exceptional cases. This matrix here is one of the exceptional cases where you cannot find, or at least they tried with a computer, and they couldn't find a modular sum, no B's nor C's that make this as a modular sum. Our theorem, well, our sum is not of this form, but it's a linear combination of 3 sums of that form. Actually, it's 2 sums of that form. So our theorem is saying, well, if you actually relax a little bit the NAM conjecture, you can get linear combinations that are modular. And this is surprising. When I first sent this to Swaggers, Sanders told me that he was very, very surprised that such an identity could even exist for that matrix. I mean, this matrix was exhaustively studied by Zagier and his students. So that's a nice consequence. That we should probably be looking at linear combination of NAM sums. Another ways of extending our result is, well, this is a theorem, this is not a conjecture, is that the Virasoro algebra, that central charge has 3 representations. I already told you 2 of them, the even part and the odd part of the free fermions. And there's another one that you can get from the twisted fermions, and we find also 2 rank 2 NAM sums, linear combination of NAM sums for the same matrix. So the same matrix gives you the right character formulas for the Virasoro in fermionic sum form. Mind you though, we did not, and I'm not sure how easy or hard it is, find monomial bases, whatever that means, for the modules. So the partitions that are counted by these sums, we do not know what they are. That's probably a nice problem for, well, that's probably a horrible problem for a grad student, but it's a doable problem for a grad student. Okay, so now I'll just shift. Before it was everything elementary, now I'll require you guys know what a vertex algebra is, but I think everyone in the audience knows what a vertex algebra is. So every vertex algebra, V, comes with a filtration like the one that I was using, and the associated graded is a differential commutative algebra. It's graded, and the derivative has degree 1. You can take the C2 quotient of that algebra and take the free such commutative algebra. So by definition, your differential graded algebra is a quotient of that free algebra. The question is, when is that kernel finitely generated? And this is the only thing that I care about. I couldn't care less about Grobner basis. I care about when this kernel is finitely generated because we can prove statements about the chiral homology of an elliptic curve with values in the vertex algebra whenever this kernel is finitely generated. When this happens, we can say nice statements about like extensions of modules producing classes on that chiral homology. So the understanding this kernel gives you deep homological information of the vertex algebra that goes away from Jou's algebras. This is something deeper than Jou's algebra. However, the easiest case, the easiest unitary case after the Ising case is this Virasoro 4.5. I've been running a process in parallel since July 26 on a computer, in a supercomputer at IMBA. Well, I'm not sure if 192 cores counts as supercomputer, but it's been running for a long time now and it doesn't converge. So we know that that thing there has more than one generator. It has generators up to degree 41 at least. I know there has one other one in degree 43, and I think I'm not gonna see the form of that generator in my lifetime. more questions along those lines. So I think it's a deep question to try to understand the kernel of that isomorphic, of that surjection. We call a vertex algebra classically free when that kernel is 0. That was the original question that I think the first one that got interested in these kind of questions was Tomoyuki. Clearly, universal chiral envelopes, universal affine algebras, universal W algebras are all classically free. This is trivial. Affine algebra for SL2 at integer level is classically free. That was in our paper. I think, again, Jethro might know this better. I think it was claimed for affine algebras at integer level, for general affine algebras at positive integer level. I'm not sure. What is easy to prove, and it hasn't been written down, is that the Hamiltonian reduction of an algebra is classically free if the affine algebra is, and the reciprocal is not true. This I already know. For SL2 at this admissible level, the Hamiltonian reduction is one of these Virasoro modules that Feigin and Prenkel did, the P prime being 2,5. That one is classically free because of Feigin and Prenkel's result. And the affine algebra, I know it's not classically free. This is a very interesting problem, again, for a grad student, try to find the kernel in this case, or already in the case -2 + 2/3 is a very nice example. What we do know is that whenever P is bigger than 2, this affine algebra is not classically free. And for P equal to 2, we do not know. And it's an interesting question. Oh, I'm sorry. For P is equal to 2 and P prime is equal to 3, we do not know. And I hope it is. I think it is. All right. So here are some conclusions. And I have something more about partitions, but I won't tell you. So we found some monomial bases for the Ising model. They're a horrible monomial basis, but it was really surprising. Well, after the answer, it's not surprising that this wasn't known because the answer is horrible. But it's something as basic as the PBW basis for the Virasoro representation, the easiest representation of the Virasoro, wasn't known. We found Q-series identities that are of the form of the Rogers-Ramanujan. They generalize this Jackson-Slater's. Well, it's not generalized, it's not the right word, but they generalize in some sense the Gordon's Rogers-Ramanujan in the sense that the P is equal to 2 case is the Gordon's Rogers-Ramanujan identity. We proved that that kernel is generated by only one guy and no, and its derivative and nothing else. I think Andrew Linshaw was the first person that asked a question along these lines. When is this kernel finitely generated? And now that I mentioned this, I passed by this. So Andrew and Tomoyuki have a paper where they prove also Hamiltonian reduction for SL3, and this is not, this is sub admissible level. And this one is not classically free. So I suspect that SL3 at boundary admissible level, so -3 plus 3 over whatever, over 4 in that case, is going to be classically free. So they got the last case that is not classically free. Okay, so that's the reference, and I'll just stop right here because these are my 15 minutes.
Oh, sorry, Raimundo. My internet kind of collapsed when you were finishing. Thank you so much. Let's clap for Raimundo. Are there any questions for speaker?
I have 2 questions, loosely related questions. Do you know any example of a simple vertex algebra where the singular support, where the associated graded algebra is non-reduced? And second question is,
yeah, go ahead.
Yeah, what I'm actually more interested in is the question of whether these elements in the kernel, so you have this map from the functions on the arc space to this associated graded, it can have a kernel. Do you know any examples where the kernel is not a nilpotent element?
When the kernel is not
nilpotent. So of course, in the examples that you're looking at, it's always nilpotent because everything is, these are to cofinite action.
Oh no, but I think that probably is possible and impossible, right? I would expect that there are no examples, like you say, with mild conditions or like quasi-least and the kind of things that Tomoyuki was looking, right? So once you know the result for the associated variety, right, that they are isomorphic.
So yes, it's related to this question. Are there any examples that are known where it's not isomorphic as at the level of varieties?
Yeah, so that's a hard question, and and of course what you're asking is provide me a counterexample to this. No, I would expect that if you have them as isomorphic as varieties, and then of course you're not gonna see this the example that you're asking for, and I don't know. I think even Tomoyuki is asking the same question. But I think he suspects that they're always isomorphic varieties. So I don't know.
Well, I think that so you can find counterexamples if you go outside of the setting of simple VOAs.
Sure.
Yes.
Sure. Yeah.
So for differential rings, it's very wild. You can of course find many counterexamples. So something about a VOA being simple seems very constraining. But I don't understand why that is. It's just experience with some examples. But
I haven't thought about questions about being reduced or not, actually. Yeah. So.
Okay.
But
I was just curious because I thought
also.
About, yeah, I haven't thought about this.
But
for
also
a while.
The kind of questions that we're looking at are dimension 0, right?
Yes.
So you're interested in positive dimension. And
yeah, I guess part of how much is right? Yeah, how much does this whatever picture you have for this phenomenon generalize beyond dimension 0?
No, I think 0. So I think what we're the kind of things that we are seeing here are really about dimension 0, because well, at least in the case I'm interested in computing these kind of homologies, and the kind of phenomena that I'm trying to find is focused on dimension 0, because I need a bound on the dimension of the chiral homology. I need the chiral homology to be finite dimensional to be able to compute it. So if the dimension if it's not dimension 0, then I already know that the chiral homology blows.
Right.
And I have no hope of saying anything. So I'm not going to be looking into a higher dimensional example for a very long time, I think. I would point anyone to asking this kind of questions to ask you. Ask Tomoyuki, or ask Anne, I guess.
It's amazing that you guys were able to calculate this character and prove this. It's pretty impressive. Thanks. Very nice talk. Thank you.
Thanks.
I just had a couple of questions. So I think this fact that you take the linear combinations of norm sums and you get a modular thing, that's, I think, well known. I know many examples like that.
Can you send me a reference for this? Because Zweigers actually told me that it was surprising because of this. So I'll be
So the thing is that So the thing is that Nam's conjecture is not, well, first of all, it's not correct as stated. I think Vlasenko and Zweigers found counterexamples, but that apart, it's not stated in the most general form, I think, in my opinion at least. So if you just, instead of the Q Pochhammers in the denominator, if you take powers of them like Q cube or Q squared, then I know many examples. So I can tell you later.
You mean you take quantum numbers for powers of Qs?
That's right. So you take, instead of Q, 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 you just take Q, Q cube, and so on. Then I know many examples. Secondly, having
those kind of things appeared when I was trying to prove. So yes, can you send me some reference of this, or these are things that you haven't published yet?
No, I can send you. These examples are well known. I'll send you. Then the second is, I think there is some work by Fora and Trevor Welch on the combinatorial aspects of these Virasoro minimal models. I've never looked at it, but I think Trevor Welch has some paper where he gives some path models or something. I don't know if that relates to your partitions, but maybe
Yeah,
it's...
so to our partitions, no, but so the thing is that I've seen these papers.
Okay.
Because the character is given by this these Hirschhorn's partitions. This count,
Right.
one of these
Yeah,
identities counts is Hirschhorn's partitions.
Yeah.
And those have a combinatorial interpretation as lattice paths. So what they did is just, well, because lattice paths come from this Bethe ansatz kind of stuff, and they just produce a partition, a lattice path counterpart for Hirschhorn's partitions.
I see.
So I tried to use that to prove our theorem, but our partitions are not counting those lattice paths. So
okay, yeah, that happens. Then the other two minor comments, or one is that this Ising, so you mentioned E8, and turns out that these are also related to characters of the twisted affine algebra A22 at level 5. There are 3 modules there, and I can tell you later how. I mean, it's exactly these identities. So that was one comment, and the last one was that you mentioned that you had recurrences with 2 variables. And actually, in general, that's a good thing, because the more variables you have, the better it is, because you can manipulate it a lot and then finally set one of the variables to 1.
right.
That's how I think recently many identities were proved like that. But of course, it depends on what you're working on. And
correct. But I'd like to make a comment actually on that. Now that you brought this up, let me go back a few slides.
Yeah.
And I might be so stupid that I didn't here. So if you multiply this thing by T2, 2K1 plus K2, that is the partition function for partitions of N with well, that counts partitions with this many parts. The powers of Q counts the energy, and the powers of T counts the number of parts. So actually here you see these 2 variable kind of partition functions, and they all combine in a nice way. It's a double sum with T's to some power. So we have 2 variable partition functions for the associated graded of the Virasoro. And this is because, well, you have this extra degree in the associated graded. You have this power, the number of parts, right. now that you have the basis. There's no natural way of adding this extra variable to the Virasoro module itself.
No, so I understand that. No, I understand that.
No, but that I think is an interesting problem itself. Like,
oh yeah, of course.
We can't find these 2 variables for, and the question is, what is this? What is the role of this T on the actual Virasoro module?
No, I understand that. Yeah, just at the level of Q series, it's better to have more variables. Yeah. With that.
Sure. We spent a very long time trying to make this identity an identity of 2 variables identity. So trying to add a T to the other side to
hard.
Any of these guys.
That's not.
And that's incredibly hard. I tried a lot of things, and there are natural ways of putting T. Actually, let me mention one that Jethro found.
Yeah, for a while we.
So what Jethro decided is to grab this. Sorry.
Oh no! Yeah, no. I was about to.
Oh.
You go ahead.
So Jethro said, well, we have this beautiful thing with the 8. Let's put T to some power there, a linear term in K, right? Our identities of the form T to a linear guy, that's very common. T to a linear time, Q to a quadratic guy. So let's put an arbitrary linear guy and adjust so that it's equal to ours. And it's impressive. It gets to be like the power of T to the 1, 2, 3, 4, and 5 coincides once we choose a linear element. And this is for arbitrary Q. That they coincide as rational functions, they coincide. And when we saw this, okay, so let's prove it. Now we have a proof. And we couldn't, we spent months until we decided to check T to the 6, and that failed. So it's kind of fun.
Yeah, no, that's right. It's very hard to put T everywhere.
Yeah, and I didn't gain any insight of this problem. That's my problem with this kind of techniques, with this kind of problems, is that we did not gain any insight. I don't know how to prove the 3-5 case now. It's just a completely new thing. I think something needs in the literature to be done to homogenize this problem, or to attack it in one way.
Yeah, there is also recently some work by, I think, one of the students of the 3 people. And she actually looks at this, the Grosvenor basis, but she modifies the order of monomials. So instead of, so she looks at, I think this is Grl X or something, and then she looks at just Lex or something like that, and she gets different descriptions. So it's even interesting in that. But I think it's hard to do in this problem, to change the order.
For which problem did she look?
I think she does it for what would be your Virasoro 2, odd.
Ah, interesting. I actually looked into that.
It's not easy. If you change the order, it's not easy.
Because it's not a global order, right? So Lex is not a global order, so it's only on a localization that actually works.
I don't know a lot
horrible
about
from
that.
a computer point of view because it doesn't converge. You do get different bases. So in the affine case, I've been trying to prove for a while the affine SL2 at boundary admissible level, and different orders give you beautiful bases, not so horrible as the one that that we have here. And I can prove the analogous statement as this one for either of these bases, but yeah, so different orders give you different bases.
Any other questions for Reimundo?
Hi.
Wait, couldn't hear someone was talking to Shashank, I think. Would you mind repeating that?
Oh, that was me. Sorry, I was asking Shashank if you could repeat the reference that he mentioned.
For what?
It's about the using a different monomial order.
I think yeah. Should I mention here or should I just send you an email later?
Yeah. Send me an email. All right.
Any other questions for Reimundo? Reimundo, I can. Yeah, Thomas.
I have just a comment. Reimundo, there's a nice relation between Virasoro 3, 4, and E8. Namely, if you take 2 copies of E8 at level 1 and take the diagonal coset, you get this Virasoro.
That's how they got this identity. That's
right.
How they got this identity.
Oh, okay.
The coset model gives you this identity.
Yeah. Okay, you already know that. Yeah.
Yeah. So the thing is that before coset models existed, there was already a relation between E8 and E7 and E6 Virasoro. You expected to have this E8 symmetry on the CFT itself. So at that time, they didn't know about coset models. So they already knew that E8 played a role in the Ising model without knowing cosets. So that's what's really surprising about physicists. Physicists are impressive.
Yeah.
This is in the 70s. And this thing with the coset model is in the 90s. So this identity is early 90s. They got it by looking at the coset. It's 92, 91 actually, the original one. And Polyakov's papers are in the 70s. It's impressive.
Okay, if there are no other questions, let's thank Reimundo again. Thank you, Reimundo. I hope to see you all next Thursday at 1 for Jetra's talk. Bye-bye. Take care.
Bye-bye.
Gracias, Reimundo.
De nada, gracias a vos.